There we go. We're starting Green's theorem today. We're down to well, not too much more. Was this 15.4? We're almost near the end of the book. This is called Green's theorem. Like the color. And later on in 15.8, we will see the new and improved, well, the improved Green's theorem. The enhanced is Stokes' theorem. We'll see that at 15.8, but it's the same format. Where Green's theorem dots the curl of f with k, k is the k vector is 0, 0, 1. This is 15.4. That's what we're dotting the curl with. In 15.8, we're using any vector n. And that'll be Stokes' theorem. So understanding the process now really gets you revved and ready to go for 15.8. And the main purpose of this is sometimes integrating a line integral or integrating an area isn't that easy, but if we can integrate, like for the line integral, if we can integrate the area, or for the area, if we can integrate its boundary easier, it's a convenient means of switching. And the dg, dx, and df, dy are based on f equaling f and g. For Green's theorem. When we get to Stokes, it's all 3D. So f dot dr in Green's theorem is f dx plus g dy. So when we're looking at a line integral, we can figure out which piece is f. F is x squared minus y squared here. And g is x. So ideally, we switch this over to, or it might be easier to do this in Green's theorem. First, we got to get it to match the general form, and then we can decide on dA. So that's the general strategy. Don't necessarily pick a form right away, but just get the dg, dx, df, dy, and figure out what that integral over there is going to look like. So g here is x. If we do dg dx, we're getting 1. And if we do df dy, we're getting negative 2y. So 1 minus negative 2y would be 1 plus 2y for dg dx minus df dy. This looks familiar. Did I do this in that Cam lecture video? Oh, fuck it. We're doing it again anyways. All right.
Nothing like seeing something twice.
I guess 1 plus 2y could have been from anything. It's not like it's a super rare thing. So I'm just setting it, our dg dx minus df dy up in a general format, and then I'm going to look at my curve and decide what dA do I want to work with. So my curve has been provided as a circle of radius 3. So we could do like negative 3 is less than or equal to x less than or equal to 3. And y would have to be between the negative square root of 9 minus x squared less than or equal to y less than or equal to positive 9 minus x squared. Hopefully you guys have grown accustomed to thinking that's the shitty way to go, because the circle is really well set up for polar coordinates and it's not that hard to do. In polar, 0 is less than r less than 3, and 0 is less than theta less than 2 pi, which makes those boundaries easier. So that's the one I'm going to recommend doing. I'm going to go 0 to 2 pi, 0 to 3. Now I need to convert my 1 plus 2y into the coordinate system I'm using. So y, if you recall, is r sine theta. And dA is normally just pure dx dy. But if we're switching to polar, we need to recall our correction factor, the r. So r dr d theta. And you can see that when you do the Jacobian matrix and stuff like that, where the r comes from. I did do this. Maybe it was a different radius, but I know I've done this recently. Huh. Oh well. What you gonna do? So let's take a look at what's going on. Let's maybe distribute that r so we can see what it really looks like. James looks bored. Did I do this in the video, James?
I don't know.
What do you mean you don't know? You didn't you watch my videos? Oh, I know exactly where I did this. But I don't know that it was in 15.4. So I've got 1/2 r squared plus 2/3 r cubed sine theta d theta. Evaluated from 0 to 1 for r. I'm going to pause there.
It's not on chapter 1.
I want to put this aside and show you one thing real quick that you may not think of, but I need a little bit more room to write, so I'm going to write on the next sheet.
The plugins.
Did you do something?
Yeah, our bomb is 3 to 0, and he just.
Oh shit!
A 1 0.
I said 0 to 1. My bad. You're right. You are completely right. Let's change this. That should have been 0 to 3. So 9/2 plus 18 sine theta. That better?
Yep.
What do you mean no?
I said yeah.
Yeah.
All right. So before I go with that, I'm hoping by now you've grown accustomed to recognizing that 0 to 2 pi for sine theta, regardless of the coefficient, or we'll call that C1, is the same thing as 0 to 2 pi C2 cosine of theta d theta equals 0. If you're not used to that, let's just do a quick, and you don't believe me. Let's say you don't believe me. Let's do a U sub on either one. Let's do a U sub. U equals sine theta, du equals cosine theta d theta. When theta equals 0, u equals
Oh,
0.
Yeah. I did.
When theta equals 2 pi, u equals 0 also. So 0 to 2 pi c1 sine theta d theta turns into the integral from 0 to 0 of c1 u du. And so the limits of integration are the same. This is 0. Same thing happens with cosine. So when you see 0 to 2 pi
That was given.
with sine theta or cosine theta, this part is going to go to 0.
I thought he got that from the problem. Waited.
Does that follow?
That makes sense.
Now, the only reason I showed the use of was to present an argument that you could see worked out.
Pi is also 1, so 1 minus 1.
Yeah, see, if you did it with the cosine, it's going to be 1 minus 1. Either way, for cosine, the cosine integral turns into 1 to 1 c2u du. In both cases, the limits of integration are the same, which means there's no area. So that's a shortcut, but it's only on sine and cosine, and only when it's a full 2 pi loop. I mean, if it went from 0 to 4 pi, that would work. If we went from pi over 2 to 5 pi over 2, that would also work. But it has to be one complete loop only for the limits of integration. That you may have learned that in Calc 1, you may not have. It's a handy thing to keep in mind because it can speed up problem solving. And when you're done writing that down, we'll go back to solving the rest of that problem, which is actually pretty easy at this point. It was already pretty easy. 18 sine theta isn't hard to integrate. But when you've got a bunch of terms going on, anything that you can zero out as fast as possible just speeds up the problem.
Yes. Oh, did you do cosine data? Oh, it doesn't matter. See, I think it was really, in the end, you're just showing that
All right.
that would turn into.
See this sign, get negative 1 plus 1.
Well,
Or wait.
0 to 2 pi. Yeah, you get 0. The sine of 0, sine of 2 pi. Oh, negative cosine. Oh, yeah, you can't.
Get negative.
It's still, no, it's still turns into 0. No, Eric, you're pointing out so many corrections on him. I'm wondering when he's going to give you extra credit for all these corrections. No.
But why
Because if we integrate it, it's when you expect you find 0.
Yeah. So then,
All right.
Because look, they cancel.
argument that what we're doing
So next one.
gets rid of the negative.
What do cardioids look like?
What?
Now we're doing.
Let's see, when theta equals 0, r equals a, when theta equals pi over 4, r equals root 2 over 2a. So it's getting bigger. At pi over 2, we just have, nope, that's 2a up here. It's getting smaller. R equals a when we have theta equals 3 pi over 4. We've got negative root 2 over 2 plus 1, so it's going negative. How's that possible? Am I doing that right? No, negative root 2 over 2 is less than 1. 1 a times 1 minus root 2 over 2. And when theta equals pi, that's when it equals 0. So what does that picture look like?
Oh my gosh, that is I don't worry, I can barely read it myself up here.
I'm just making I'm picturing what the cardioid looks like while you guys are doing it. I'll go over to Desmos. Let's go look at Desmos, see what this looks like.
Had on the chest and I'm like, so let's take a look at Desmos.
If
Let's
okay,
learn
I'll write it in something you can see a little bit better. No, I was showing you what to do when you don't have Desmos. You make a fucking table. Theta equals, r equals, and calculate. When theta equals 0, r equals 1 plus cosine of 0 is 2, r equals 2a. So you make a table and plot points. Let's say that's a and 2a, so when theta equals 0, we're there. I was doing that. You don't need Desmos to graph. You guys learned how to graph.
We don't.
Yeah. Willow let me use R. How do you convert to polar in this?
Go to the wrench. The wrench.
I hit the wrench.
Great.
There you go.
Oh, that was just. Something one font.
The whole time to do that. I know, right? I know this, man. I had no idea where we're starting.
I think I learned that like.
So that's what the cardioid looks like. We're doing something like that.
Like in high school, someone showing me that. I mean, you're not wrong.
Okay, so having that in our head,
We will have a bit better.
let's just sketch the picture. Cardioid means heart, so I knew it had a heart shape, but I wasn't sure exactly how it looked like. I don't know that that line integral is going to be fun in any way, shape, or form. I don't even know that that area is going to be fun, but I at least in the area we could shift to polar and use polar coordinates. So let's see what we can do. So this is my F and that's my G. So dg dx is -1 and df dy is 1. So the surface integral would be dg dx minus df dy dA. And we have -2 dA. So if we switch to polar, it's 0 to 2 pi, and r goes from 0 to a times 1 plus cosine theta. I'm going to put the -2 out front. And so my dA in polar is r d theta.
good. Well,
All right, so we start integrating.
So it's just a line, that's the line that loops around.
Yeah.
Shapes.
The curve is the line going around the cardioid.
You just make it an area, because that's what it is. Continuous.
All right, so the -2 and the 1/2 reduced to a negative. We got a negative 0 to 2 pi.
This is in
And I've got a squared times 1 plus cosine theta squared. And I want to write out that last thing. A is a constant. I'm going to factor out the a too. I'm going to put the a squared out front. And now we just have 1 plus cosine theta squared inside. That's 1 plus 2 cosine theta plus cosine squared theta d theta.
That's how you.
Okay, so that looks kind of crappy. The cosine squared kind of sucks, but recall cosine 2 theta is 2 cosine squared minus 1. So cosine squared theta is 1/2 times 1 plus cosine 2 theta. And we can make that substitution. And if I do, plus 1/2 plus 1/2 cosine 2 theta d theta. So we don't want to do all that work. What ones go to 0? That goes to 0. And that goes to 0. Because 2 theta would be 0 to 4 pi. We're still getting back around to where we started. So both of those go to 0. We just have negative a. This all boils down to negative a squared, 0 to 2 pi. 1 plus 1/2 is 3/2 d theta. So we have negative 3/2 a squared times theta evaluated from 0 to 2 pi. Now the negative sign may bother you, but we're not doing area. We're doing this line integral, and this surface integral was -2. So we should have expected we know the area is positive. We're multiplying it by a -2. We should end up with a negative sign. Does that make sense? It doesn't check the math, but what I was just trying to argue was if we know we have -2 dA as our surface integral, I got -2 times the integrals for dA. Area is positive. I know that's a positive value. So -2 times a positive value is going to give me a negative value. So I at least have a negative value, which bothered me at first, but when I look at the integral, it makes sense.
It's not the entropy. I'm assuming so. Last night was the late turning. I didn't check. Like he usually sets it. I worked so hard on the reader and I didn't even get turned in. See how wrong you were? Yes, where I submitted it.
You guys ready for another one? I know Lawrence gets a little moody unless I put some physics in here, so maybe I better throw up a work problem. Start telling me vector fields are pointless unless they're physics related. And I don't really have a good argument against that, but working with vector fields that are not physics related are good practice. I looked up conservative vector fields, and the only ones that we really have for examples are all in physics. But vector fields in general are everywhere. The wind over the planet makes a vector field. You can model water over the ocean with vector fields. There's vector fields everywhere. So if we're not working with conservative, vector fields are all sorts of places.
Crowds of people.
All right, so I gave some time to write down the problem. That should say counterclockwise. And I'm going to draw that domain so I can see what we're looking at. So I got X and Y. And Y equals 0 would be the x-axis. X equals 2 is here. And 1/4 x cubed is goes like that and like that. Let's see where it crosses the x equals 2 line. If I plug in 2, I've got 2 cubed is 8 times 1/4 is 2. So it's crossing at 2. And so the region being captured is here. So we have a couple options. Work is the line integral. In this case, a closed line integral, f dot dr. And if we go around the curve, we're going to have three sections to look at. Because C is going to be C1 plus C2 plus C3. Now, this is entirely doable. I just don't know that I want to do it. Breaking it up into 3 integrals kind of sucks. So if I wanted to switch to, if I wanted to integrate over the area rather than the line integral, I can do that by adding an integral and adding a derivative. So we'll have the integral with a dA. And to do that, we need dg dx minus df dy. So f is square root of y, df dy would be so 1/2 root y. So this is 1 over 2 root y. And dg dx must be 1 over 2 root x. dA, or that surface.
I have like the square root in here that he doesn't have. It's like maybe.
I don't like the square root on bottom. I'm going to move it to the top and use negative exponents.
You actually like the blades. Instead of like, I actually got a wire. It's just- it's at least it's working the blades.
You know, the problem is you gotta- you gotta do that, is get a reach, get a high, get a high, and get you- Get some fun, that's it.
Or just drop the homework solutions. That's what I like.
All right, so what are we going to use for dA?
Yeah, exactly.
Use for E and A and say
We can go if we can go, I think going from y equals 0 up to, if we do 0 is less than y is less than 1/4 x cubed. And then x is between 0 and 2. That might be the easiest way to do it.
Yeah.
And we're leaving it in what we have. So this will be dy dx. Still not the most lovely thing, but it is what it
Yes,
is.
question. You forgot the negative sign of the y to the 1/2. Oh, yeah, you left a negative sign off.
Thank you. So this one is just 1/2 x to the negative 1/2 y. Here we go up the power, divide by the power, plus y to the 1/2. Not plus, minus. And we're evaluating that from 0 to 1/4 x cubed dx.
So I'm kind of confused. Why do we have to do that double integral? Like, can't we just do our work like FDR across like each individual line segment? Just like
You
we were doing in
can.
chapter- Just like we're doing
If you want to
like-
do, I led with that. I said you could do that. You could.
Oh, I thought that's what,
You-
I thought that's what we're doing.
We're not doing that. We're using Green's theorem. Because the closed integral
Area. I think it seems like it's not just.
equals dg dx minus df dy.
Line makes it cheap. Is it like
DA.
significant like this way or like, I don't know.
That's Green's theorem.
Right. But I don't see the advantage of that like right now.
You have to do 3 integrals for this one. Knock yourself out. See if you get done before we do.
But you gotta do 2 for that one, so like really what you say 1 integral. I mean, if it makes a sheet, then it's fun. I'm just wondering, is there like?
Not only do you have to do 3 integrals, you have to set up the lines. Go for it. You gotta make a line for each thing. How are you gonna parameterize C cubed or the C3? How are you gonna set up your R? What are you gonna do? Let's finish this and let's look at Lawrence's way in next. That's a fair question. And let's look at why I don't recommend doing it. But it is very much a fair question. Can we finish what we're this way first though? Will that work for you? It's a fair question. So we have 1/2, 1/4 x cubed. That's gonna make that a 1/8, and x cubed, this is gonna become x to the 5/2. And if I plug 1/4 x cubed into the square root, I'm gonna get square root of 1/4 is 1/2. And x cubed to the 1/2 will be x to the 3/2. Yeah. So if I go upper power, divide by the power, multiplying by 2/7.
Because they're multiplying x and then 1/2. And the 6/2, 1/2. Yeah, but remember, we're plugging in the y. Plugging in the x to the y.
The exemplary.
Plug in the 1/4 x to the y.
The exemplary.
Get it?
Not really. I mean, you're plugging it in, but let me see what you got.
So this is 1/4, 1/28.
It'd be like Carlos.
I'm not just like that. 5/2.
This is 2 cubed times square root of 2 minus 1/5 2 squared times square root of 2. So that's 8/28, which is 4/4. Let's see, divide by 4 is 1/7. 1/7 root 2
Like he just like substitute.
minus 4/5 root 2.
He put, they're just. He did it, okay.
Yeah.
He literally, okay.
Yeah, you just put them in and
Okay.
multiplied the letters together. That's what we got it.
I must be doing this, so, okay. Thanks, bro. Don't worry, it's fine. Yeah.
Sometimes we find that 1 divided by 1 is 0, and sometimes we find that 1 divided by 0 is still 0.
Or if it's coin, it means infinity.
Yeah, that's what I got.
Did you say, yeah, that's what I got? You are such a liar. I know you didn't do the curve. You're
Yeah.
so full of shit. It's funny though. That's funny.
Say it again.
That made
Two
me
what?
laugh.
As 2 cubed over 28.
Are we gonna go over?
Which part?
The 2 cubed over 28.
Oh, that should be 8. It'd be 8/28.
That should
So
be a
what is down in your
2/7.
math? Would you double check it?
Yeah, that's a 2/7.
There you
I
go.
got hasty. That makes this a 10. That makes this a -18. Good catch.
What?
All right, so I'm gonna rewrite this problem down so we can explore it doing the line integral.
I said to be counterclockwise. We're just talking about that. You can just going clockwise, you can say it's going counterclockwise, backwards, and negative. We can have both lines that are counterclockwise because the order of this. That's why it's just a negative.
All right, you guys ready to take a look at the line integral? See if we want to do it.
Yes, sir.
Okay. So I redrew the picture. Let's slap on some points. We know this is the origin. That's an easy one. This was 2, 0, because that was the x equals 2 line. And this is 2, 2. So if we wanted to do the curve along C, let's call this C1, C2, and C3.
You just combine them together to make your area. That's all green clearness.
So C1, you got to do R of T. We can, for C1 and C2, we can do the R of T equals, as a reminder, 1 minus T times R naught plus T times R1. We can do that for the first two, but not for the third. Unless we can show this is a conservative vector field. And then we can choose any path we want. But if we know, okay, it's a conservative vector field, we already know the answer. And since I didn't get work equals 0 on the other way, I'm pretty sure it's not 0. So I'm pretty sure it's not conservative. So we've got 1 minus T times R naught, which is 0, 0, plus T times 2, 0. So R of T is
That might work in physics on this class.
0 and 2T.
Yeah, the problem would say let the vector be conservative. The second vector be conservative. Vector be conservative.
So dr is 0 and 2, which means the line integral we're looking at, t's got to go from 0 to 1. We dot this with that. The x component of this is 0. The y dr component, so we've got 2t to the 1/2, comma 0, dotted with 0t, or 0.2 dt. This is going to be 0. So C1's an easy one to do. Because the dot product 0. So now we take a look at C2. We set up our R of T the same way. So for my first part, I've got 1 minus T times 2, or times 2, plus 2T. And then I've got 2T for Y. This looks like I end up with just 2 comma 2T.
Yeah. DR is 0.
So dr is 0 and 2. If I want to rewrite f, what is f in terms of R of T? I have the square root of y, which is the square root of 2t. And the square root of x is the square root of 2. This is already more work, I'll have you know. We haven't even gotten to the curve. We got 0 to 1, f dot d.
But you wrote, I was wondering if there was like a step I missed or something. You wrote 0 to T, R T is equal to 0 to U, and before it looks like it should be 2T 0, but it would still work out to 0 anyway.
Did I put it in the wrong order? I fucking
Maybe.
put this in the wrong order earlier. Yeah, this changes. This changes everything. That would be 2, 0. So this is not 0.
RIP.
Anybody who's able to
So we won't even we're not going to evaluate yet. We're just going to set up the integrals and show that there's a lot of work. Because we're running out of time already. So this is dotted with 0, 2.
Yeah, but like this I can follow it. At least it's more work, but it like at least makes sense, like what I'm doing.
You're gonna need to learn the other way. Because Green's theorem and Stokes' theorem are almost identical. Just because you have more experience with line integrals. It's a formula that you have to memorize for Green's theorem and switch with.
That's the problem.
That's how a lot of harder calculus problems are solved. You can't always do the line integral. This problem you can, but you can't always do it. Could you have done the line integral on the cardioid? How would you parameterize the cardioid? So you're going to have to learn the Green's theorem. So if we did this one, we'd have 2√2 dt. And we can go through and do that one. That should just get you 2√2. Curve 3 is the pain in the ass. My initial thought to parameterize it would be to set x equal to t, so that y equals 1/4 t cubed. And that would make, so r is t and 1/4 t cubed. dr is going to be 1/3 t squared. And let's see, we started at 2, 2, and we're going to 0, 0. So the limits of integration here would be going from 2 to 0. So starting at 2 and going to 0. So y to the, we got to do the f goes y to the 1/2, x to the 1/2. I got to write this in terms of that. So y to the 1/2 is, I'm just going to write it. We can simplify it a little bit. It does simplify to 1/2 t to the 3/2, but I want to make sure I don't lose anyone in the room by going too fast. Dotted with 1/3 t squared dt. So we still got this integral to solve. We got to do the dot product out. We got this integral to solve, this integral to solve. We've already done twice the amount of work and we don't even have the solution yet.
Sometimes the hard paths are the best.
So
It might be, you feel the most rewarding, but they're certainly not the most time efficient.
The world's ending and you need to do this. You need to solve the problem.
What do you mean it's going to take you 2 hours? You have Green's theorem.
oh, I might flat out just specify I want you to use Green's theorem. Or Stokes, because that's the point. You're supposed to learn the calculus. You're supposed to learn the tools in the class, not just go, I don't want to do that. That's too much work. And Lawrence, you're capable. You're not a fan of formulas. Well, no one's a fan of formulas. Well, maybe James might be a fan of formulas. He's got that formula look to him, doesn't he?
Wow, now you're just calling them basic.
So it's 9 o'clock. We'll do more Green's theorem tomorrow. And then we'll dabble in surface integrals.
Yeah, you can only like derive math to third point, and at some point you have to memorize some of it.
Yeah.
It does suck.
It's actually not that hard.
No,
You
it's
want-
not.
I just can't trust my memory, that's the problem.
I totally agree. I don't trust my memory that much either, but there are gonna be times when you have to remember it.
Number one case of memory is when I put the solubility rules, which is right after. Like, oh, I put the
I think,
solubility rules.
Lawrence, I think the key is just practice. Just keep practicing it long enough and you'll remember it like naturally.
Oh, no, sometimes like this will come, it's like 60%. So I have to like.
It's deliberately why I told you the conservative field test was set up the same way. The conservative field test is dg dx minus df dy equals 0. You memorize this, that it's the same formula.
You have a blessed day.
You too. Have a good day, guys.
Oh, you're talking about this. You're talking about couch.